Welcome to MEE Live. I'm really happy today to have Ludmilla and Victoria with us, who are going to talk to us about their new R package, estar. So I'm going to hand over to them. If you have any questions, we're going to do questions via the chat. So do feel free to start posting questions in the chat whenever you like. I'll ask the questions at the end because I know sometimes it takes a while to get the typing done. So do feel free to ask questions at any point and we'll ask those questions all at the end. Okay, so with no more fanfare, I'll hand over to Ludmilla and Victoria.
Thank you, Natalie. Let me get you my presentation going. Yes, so sorry for that. I will present you what estar is, a bit of the rationale behind it, and a couple of the functions. So let's go. I don't know how familiar you are with the discussion behind stability, the discussion of ecology and stability in general, but there is this. It's years to come, so it's been decades that people have been discussing what is stability and how to measure it, and there have been attempts at summarizing it, but there was this very nice publication by Grimm and Wiesel in 1997 that found basically 163 definitions of 70 stability concepts. And this was part of our motivation, right? Because even when I was writing the paper, whenever I would talk to people, oh, I'm writing this package about stability, they would always come with a preconceived notion. Oh, it's resilience, then it's this or that. So this was a big motivation for us to say, okay, can we boil down to how many metrics and can we focus on them and can we make them available for people to use, right? So there was this idea of calling it a Babel, because everybody's talking about stability, but there is no defined concept for it, like a single common denominator, right? And speaking of that, we actually want to establish early on some definitions that will be useful for all of us to know. So throughout the presentation and also in the paper, you'll see whenever we are talking about a system, this is something we want to measure the stability of. And it can be at different ecological levels. It can be a population, it can be a community, it can be a whole ecosystem. There is always something you can monitor that you can determine the stability of. There is a state variable, is something that we need to calculate stability, is the variable that somehow reflects the stability of a system. It could be the abundance of a population, it can be the species richness of a community, it can be stress hormone level of an individual. So you can imagine that as those change over time, they reflect somehow the state of your system. And then there is the baseline, which is basically the reference of your system. And this is what you would imagine to be reflecting the dynamics of a system when it's undisturbed. So it's in its natural, so quote unquote, natural state, how it would look like. And this is what we often compare to, what we compare our disturbed system to. And besides this, so various definitions of stability, all these concepts, there is an actual foundation for it. There is a good justification for it. And this was brought into light by studies by Ian Donahue, where he identified that stability is actually a multidimensional concept, whereby you have several aspects of stability that actually should be measured in order to have a full description of that system. And what it means is that here we have two opposing cases in the sense that if we think about these three metrics that exist out there, so variability, robustness, and resistance, They can be very highly correlated, meaning that if you know one of them, you kind of know the relationship of the others. But there is occasions where, depending on the system or depending on the type of disturbance that is applied to the system, there is low correlation between them, meaning that by knowing one of the variables, you actually don't know how the other behaves, which means that you should address both of them. So it's not only that ecologists were lost in talking about stability in different ways. No, it was there was a good reason for it because they brought different information about the system. And very interestingly, and also a big motivation for us was the fact that different types of studies were looking at different types of metrics. So this is a very nice graph from Donahue, where you can see that experimental studies, and observational studies, they often address variability, whereas theoretical studies not so much is represented in there. But if we think about asymptotic resilience, and we're going to talk about all these metrics later, they're mostly addressed in theoretical studies. And we're like, okay, if addressing multiple aspects of stability is so important, we would like to see them applied to the variety of studies that we can have in ecology, right? So we would like to have a balance in this graphs. And so this was another motivation for us to come up with a toolbox basically that brings together the metrics that are most often used. And this is how we wrote estar. We went after the metrics that are used in the literature, in experimental studies, and we wrote functions where you can apply them to realistic data. And this is what I'm going to guide you through now. So as I said, we have a toolbox, right? So I'm going to present to you the contents of this toolbox in a sort of in by parts. And we start with the functional metrics. They are those six. And the basic idea of what we refer to as functional metrics, they are metrics that you need a time series data to calculate them from. And this time series, as I said, it is a group, right, of functions. And all these functions, all these properties of stability, they have slight varieties between them. So there are several ways of calculating invariability, resistance, and so on. And the time series that you use as an input to the function is already a determinant of the type of variant you're calculating. And by this, we actually use the function, so syntax to identify it. So you'll see later that all of our functions, they have their names. So here represented by metric. And one of the first arguments you have to give is the type of metric you want to calculate. And this identifies a subgroup of variants where you either calculate a, so to say, true functional metric in the syntax of our package, where here you're expected to give a time series of a single state variable. And as I said in the beginning, this can be population abundance or some trait value, or you give compositional time series. And this is based on your composition of your community over time. And the metric to calculate is based on community dissimilarity. The second way to identify specific which metric you want to calculate is by identifying the response. And you can think of response as, okay, the way you measure how your system is differentiating between how your disturbed system, is different in relation to your undisturbed system. And this can be by the variable itself. So if you keep thinking about population abundance, you can think how much of a drop there happened. Or we can also scale that response by addressing, for example, by using the log response ratio between your disturbed state and the undisturbed state, and kind of scaling your response with that. Um, and another possibility is by doing the difference between your disturbed and your undisturbed states. And as I said, these are possible arguments that you'd give to the function where you define, okay, this is how I want to address this is how I want to measure my stability. This is how I want to compare my disturbed and undisturbed systems. Sorry. Finally, we have another common argument, and this is the metric time frame, which is basically, okay, where in your data do you want to measure all this metrics for? Because you can imagine your data might contain data from before your disturbance, but then you define, okay, I want to measure this. This is the time reference where it's relevant to measure my stability for, and this is also an argument that appears for all of the functions. Finally, we come to how do you get data in estar, right? And we can have, so to say, a dream scenario where you have an independent baseline and independent disturbed data. Imagine you have a case where you followed a system that has this is the case for many experimental settings, right? Where you have a control where nothing is disturbed, and then you have the disturbed cases where you apply your disturbance and see what happens. You can have basically separate data frames for them, or even the same data frame with both time series of baseline and disturbed scenarios, and you give them as an input. You tell this to the function, or you can have a scenario where maybe you're monitoring a single environment, and this is the case for a lot of field studies, right? Where you have data on a field season or some river, some lake, and a disturbance happens as you're monitoring it. So you might have a time frame before your disturbance where you can say, oh yeah, this is how my system behaved before, and now I have new data for that same system. This is the disturbed state. And you also have a function where you define it based on your data. You just have to tell, okay, what is the time frame for which I have a baseline? What is the time frame that should be disturbed? And finally, you give this all as arguments for the function. You give the name of your data frame, you give the name of the state variable inside your data frame, and you give the name of the time variable inside your data frame. And there's something I forgot to say, I'm sorry. This is all for what we call the functional metrics, right? The ones that are based on a single state variable that you're going to compare across two systems. If you want to go and measure stability as a change in your compositional of your community, then it's relatively simpler. You need to have the data, your a time series of your community composition for the disturbed and for the baseline systems, and you give them as input. The way we calculate community dissimilarities based on the vegan package. So you also can define which type of dissimilarity you want to calculate, and whether you're standardized for presence absence data. But you can see it's more straightforward. And I'm going to show you here how it looks like when you apply star to a data set. And this is the data set we use in the paper. It's basically a mesocosmo experiment where we had 128 species of aquatic microinvertebrates, and we split them into functional groups just to make it easier to analyze. And we applied different concentrations of an insecticide. So here at this vertical gray line, we can see when the insecticide was applied. And we followed this group for 56 weeks, sorry. And we're going to compare how they behave under the low concentration, which is 0.9 micro liters per liter of water with the 44, which is much higher concentration, and see how we can measure stability in different ways. Here, just going through what the function looks like. So if we take invariability as an example, invariability you can think of as how much your system is going to oscillate after a disturbance. And you can think that the larger the magnitude of your value, the higher the stability. So the function always spits out a value that you can interpret according to the tables we provide in the paper. Stability, as I said, this is literally what the function looks like. So you define which type of response you want to, which type of metric you are addressing. So in this case, it's a functional. We are using a single state variable, right? We'll use the log response ratio as our response, as our way of comparing the disturbed and undisturbed states. For invariability, there is a special argument called the mode, in which you define, which again, yet another variant of invariability, where you can choose to measure invariability as the amount of residuals in a linear model that you fit to your data, or it can be the coefficient of variation of your data after disturbance happens. In our case, we use CV because this will measure invariability as the coefficient of variation. And finally, as I said, you choose the time frame for your metric when you want to measure it. And here, all these other arguments are the data that we include in the package that you give the names of the data frames and the variables inside them. For when you're measuring compositional stability as a measure of compositional dissimilarity, you just give the type name, you define the time frame, and you give the data. It's much more straightforward, as I said. And you're going to evaluate how much it changed over time as we established. I'm going to go through all the functional metrics, so to say, present them, and then we do a bit of a recap of how they look like for our data, right? I'm going to show you what the function basically looks like. So resistance is the second functional metric we have. You can think of it as this drop that happens in response to a disturbance, and it can be measured as in two ways. Either you can measure it for a defined time step. So here I look at the first time step. And for this, you have these two special arguments where you say, okay, I want to look at resistance at a time step defined by me, and it's going to be the first time step after my disturbance. Or you can ask the function to look for all your time frames for a given time frame. You can see, okay, what was the maximum change in my state variable? And you can imagine that the way you interpreted it is that the maximum resistance is at 0, meaning your system didn't change, basically. And if you have higher higher values than 0, then you have under or overcompensation of your system. And again, this is how the function looks. So this 3 points means that you still define your type, your response, but you add these special arguments, and then you still need to define how the data looks like. Recovery rate is our third metric, and this is basically the slope of a linear model that we fit to your response. As I said, in this case, we're using log response ratio. It can be, you have other options, and for the community dissimilarity, the same. But you see that the line we fit, it goes in the other direction because it's dissimilarity, right? But you can think that for both cases, the higher the absolute value that the function calculates, the faster the response. And here we don't have any special arguments. You just define the type, the response, arguments, and the metric, and the slope will be calculated all the same. Then we have recover extent, which you can imagine it's like, okay, at a point that I say, the user can say, this is when I expect my system to have recovered. I'm going to check how close it is to my defined, to what I would consider it to be recovered. And you can imagine, sorry for the typo here, but you can imagine that the maximum recovery happens at zero because it means that after all of this, your system is back to normal. It's back to, there is zero difference to its undisturbed state. So this means maximum recovery. And again, if it deviates from zero, you either have a system that overcompensated by having your variable go higher or under if it's lower than your undisturbed case. Then we have persistence, and we measure persistence as a proportion. So it's a value that falls between 0 and 1, and it's a proportion of time that your variable is stayed inside a limit. If we're talking about functional resistance, again, if you have a single state variable you're comparing, the way you define those limits is by calculating the standard deviation above and below the mean of your baseline. And then we check for the the response time of your system. How much time did your system stay inside that limit? And you can imagine that, so it's a proportion of time. If it stayed inside the whole time, it means your system is pretty stable. If not, then you see how far it got, how close to zero it got. And for if you're measuring compositional dissimilarity, however, the limits of what defines your system as being persistent or not, we ask the user to give because we understand that a community dissimilarity cannot be as easily summarized by a standard and deviation. So we ask the user to say, okay, how dissimilar would you admit your community to be before saying it's not the same anymore? So the user is expected to give those values with the low lim and high lim arguments. And finally, we have the overall ecological vulnerability, the OEV metric, that measures the area under the curve of your response. And this is a metric that you can think of as encompassing all the others, because you can imagine that if this line, as the way this line shifts, meaning that if you have a lot of variability or if you have a fast recovery, or if you have no recovery at all, the area under this curve is going to summarize all these behaviors, right? So this is a variable that it's always bigger than zero because it is an area. And the higher the variable, the higher the value that the function spits out, the less stable the system, because you can think there's a lot happening here. Sorry, in this curve, right? And again, there are no special arguments. They are the common arguments that follow for all the other functions. So let's see what results we got. Here I present the most interesting one, so to say. So for invariability, if we look at the detrivores in the high concentration, we see that actually they have a higher value of invariability despite this big drop. Here they have higher invariability than before, than in the lower concentration. And this is interesting because you would imagine just by looking at it that this big drop means, oh, it's varying a lot. But if we actually look at in lower concentration, the variation, it plays around more with how it behaves around the mean. And we think this is some interesting that the metric can capture this, that a visual inspection would make us think this way, but when actually calculating it, we see that it's something else. And also for the whole community, if you see those low and high values, they are what we calculated with the compositional dissimilarity. We see that actually the system is actually a little bit more stable under the higher concentration of the insecticide, sorry, which is an interesting idea to have, right? That a higher concentration, the stability, the community actually respond a little bit more stable than if we look at individual groups. For the recovery extent, so how much our system managed to go back to its previous state. If we look at the functional stability of the groups, so the carnivores, the detrivores, the herbivores, we see a lot of negative values, meaning that there was a bit of undercompensation, right, for all the groups. But if we look at the community itself, we see a little bit of an overcompensation, meaning that the community as a whole behave differently than the groups themselves. So it's an interesting, it's again to that idea of, okay, you need to consider stability from multiple perspectives in order to give a proper diagnosis of your system, right? The same for resistance. We see a lot of negative values, which this is what, if we had only calculated stability from a single variable, this is what we would have addressed. We would say, oh yeah, the system seems to be undercompensated. But again, if you look at the compositional of the whole community response, is actually a bit of an overcompensation. And finally, for the overall, the summarizing metric, when we look at the overall ecological variability, we see very illustrative for the detrivores, for example, how under a high concentration of the insecticide, we have this bigger area, and how it shows this. So this big drop plays a role here, and also for the herbivores, quite high value that is calculated because of this curve that varies so much, right? But we see much less variation if we look again at the whole community. So this is just to reinforce the fact that depending on how you are addressing how you're quantifying stability, you get different information, and how estar allows you to actually calculate it from different perspectives, and then compare and see what makes sense for your system or not. So that was it for the functional metrics. I'll transfer it to Victoria now for the Jacobian metrics.
Thanks a lot, Ludmila. I will take over here. Try to share my screen. Just to confirm, do you see my screen well?
Yep, that's perfect. Thanks.
Thank you. Okay, so thanks a lot, Ludmila. Ludmila has presented to you one set of functions that we have in estar, functional metrics, so functional stability metrics, and I will focus on Jacobian stability metrics. And Jacobian stability metrics are those that were mainly used by theoreticians up to now. So in that figure, in that plot by Ian Donoghue and colleagues that Ludmila has already shown, these asymptotic stability properties that Donoghue call asymptotic, that's what we call Jacobian. So we hope, we had difficulties choosing the name actually, but we hope that's the name that is suitable for this group, because basically these all metrics that require, why do we call it such, is because all these metrics require Jacobian matrix as an input. And Jacobian matrix is also known as interaction matrix. It describes interactions between species in the community. So you can see an example, a simplified example of such a Jacobian matrix here. And each cell, the value in each cell reflects the effect of the abundance of species in the column on growth rate of the species in the row. So beta 1, 2 here reflects the effect of the abundance of species 2 on the growth rate of the species 1. This is for the interpretation of the off-diagonal betas, and on diagonal, we have the effect of the population abundance of the species on its own population growth rate. So that's what's commonly known in population ecology as density dependence. So this matrix B, also known as Jacobian matrix or interaction matrix, is the main input that is needed to calculate what we call Jacobian stability matrix. I hope I'm clear with matrix and metrics is not always obvious, but yeah, so how do people get the interaction strands from the field or laboratory observation data? It differs a lot. There are different ways to get this matrix B, but we think that one of the useful and rather straightforward ways to obtain the matrix, if you have long-term community abundance data, community abundance time series data, is by using multivariate autoregressive state space models. And that's the machinery. These multivariate autoregressive state space models are implemented in the MARS package, and estar relies on the MARS to estimate B matrix from your community time series data. Of course, if you have your matrix B estimated in any other way, you can directly supply it to Jacobian matrix as give it as an input. But that's one way to estimate them by using MARS. And what are these state space models? As the name says, they have a hidden process, so a true process according to which the system develops. This describes the dynamics of the system from time t to the next time steps. And the system here is community. So the state of the community at time t depends on the abundance of species at time t-1 and some other parameters. I will describe it in a moment. And our observation process is actually the counts that we get from our system. So it inherently usually involves some observation or sampling error. So we cannot have an access to a true hidden process. Now, a bit more in detail about the state hidden process. So on the left-hand side, our XC is a matrix of hidden process abundances of M species in rows over time t that are in columns. So each column here, the first column describes the abundances at the time t for all our M species. This matrix is a function of the abundances of our M species at time t-1. That's what vector tx t-1 gives. B is the interaction matrix that we actually are up to. That's the matrix that we want to estimate for our Jacobian stability properties. And I already described that the values in this matrix reflect the effect of the abundance of the species in the column on the population growth of species in the row. Then finally, we have U. U is a vector of intrinsic growth rates of increase for our M species. They are often assumed to be zero to comply with the assumption of stationary process. However, of course, in reality, systems are rarely behaving, or rarely are found in their stationary at their quasi-stationary equilibrium, and therefore to comply with that assumption, what's often done is that the abundances are demeaned. So also something I should have mentioned, our x t-1 abundances here, these are usually locked. Our input, well, these are actually the abundances that we want to infer. We don't have access to them, but our input data that I will come to soon, our counts are locked prior to supplying them to the MARS. That's in order to comply with this multiplicative process according to which this population dynamics is developing, and therefore U then reflects the vector of intrinsic rates. So to comply with the assumption, what's often done is that our locked counts are demeaned. So what we do, we extract the mean of the time series for our species abundances. And WT is vector of process errors that reflects the effect of environmental stochasticity on our species. It follows multivariate normal distribution. This means 0, 0, and the standard deviation of Q, where Q is the variance-covariance matrix, where on the off diagonal, we see the covariances between our M species that are caused by environmental factors, and variances are on the diagonal. So this was a simplified specification of the state process. We may have a much more complex specification of this model. For example, for ecologists, it's often interesting to assess the effect of environmental covariates on community dynamics. And that's done by including a CT, which is a vector of P/1 of environmental covariate values. So examples of environmental covariates can be rain, food, and temperature. And this P/1 vector, the user supplies, and no missing values are allowed in this vector. They cannot have missing values. And then we have a matrix C that we are actually estimating, and this matrix is a M/P matrix that consists of coefficients of the effects that our P environmental covariates have on M species. So species are again in the rows and covariates in the columns. So here gamma 1,1 reflects the effect of our first environmental covariate, rain in this simplified example, on our first species. And we will have this estimated effects for each species in the row 2 to the species M. And then in the columns, we will have all our other effects of other environmental covariates estimated up to the covariate P in the last column. So I hope that that makes clear. Then WT is then, in this case, describes the residual process variance covariances after accounting for the effects of environmental covariates that we actually included here in our CT vector. And now we come to our observation process. So on the left-hand side, we have a matrix YT. It's a matrix of n observations that are, again, in the rows. And in the columns, we have time t. Now, again, we have x t-1 as a vector of our observations that we specify only for the very first initial values, so to let the model started, to get the model started. And Z is an association matrix that describes how to map X on Y. So how to map our species or our true process on our observation process. And very often we have one observation per hidden process. In that case, N is equal M, and that then Z is an M by M identity matrix, as shown in a simplified manner here. However, in some cases, one can have several observations per hidden process. For example, one can have several replicates, either in space or in any other ways of your community that you are observing, and then your Z matrix will look differently. But I don't go there because of the time constraint. It's just to make you aware. And then A is a vector of biases that offset observations from the process values. And VT is a vector of observation errors that are distributed according to multivariate normal distribution. This is the mean of Z, 0, and the standard deviation of R, which is a variance-covariance matrix of our observations. And similarly to how we can include environmental covariates and assess their effects on the community dynamics in the hidden process, we can also have covariates included on the observation process. So we can, if we know that there are certain covariates that affect sampling effort, they can also be included here. But I just show a simplified model specification. So things to be aware of if you are fitting such a multivariate autoregressive state space model is you have to think very carefully before specifying the model structure. Think about how your system functions and what main processes have to be included, because as you already grasped, hopefully, there is a possibility to specify a very complex model. So you can potentially want to or try to estimate all the Q's with all their subscripts, so the Q's and R's in the variance covariances matrices. And that, of course, will require estimating many parameters. This may lead to the fact that the model may not be identifiable. There are also possibility of convergence issues. For example, when the model is degenerate, that's the case when one of elements on the diagonal of Q or R are going to 0, but there is a workaround for that in Mars. There is an argument for degenerate cases. An important thing is that time series have to be long enough to estimate parameters, and I'll just leave it here, because now if we have our B matrix, we can then go to estimated to calculating our Jacobian matrix. We have 5 of them in E star. 4 of them allow assessing the response of the community to a pulse perturbation, and the 5th one assess the responses to the white noise. So I already explained that one can use Mars that is embedded in E star. So we basically call Mars from E star if the user specifies, gives as input a community abundance time series to then extract B from that fitted model object. And then B, this matrix B, is the only input that is needed for all of our Jacobian metrics. Now, each matrix has the name that is, the function has the name that is very similar to the metric itself. So reactivity is exactly called like that, and we only give as input our matrix B. And reactivity is the maximum instantaneous rate at which a perturbation can grow at the moment of disturbance. We here show a visual representation of what that may reflect. This is a very simplified, I would like to draw your attention to the fact that this is a very simplified representation because we try to capture it as a univariate, so as a time series of one variable that responds to a disturbance shown here in gray, but of course, oh, sorry, I hope that was not too loud. There is the balloon that exploded here. But of course, what we are measuring actually is the response of the community that consists of multiple species, and this multivariate structure of the community is grasped by the interaction matrix B. So how do we interpret reactivity? If it's more than 0, then the system is destabilized, and if it's less than 0, it is not. The second metric, Jacobian metric we have in E star is maximal amplification. It's the largest factor by which a perturbation is amplified by the system. If it is close to 0, then the system is stable. And if it's much larger than 0, the larger the one it is, the larger the one it is, the stronger system departs from equilibrium. We can have initial resilience, which is initial rate of return to equilibrium. It's interpreted in the way that the larger the value, the more stable the system, because the larger the value, the quicker the system returns to equilibrium in a short term, because that's the initial rate of return. We then have asymptotic resilience, which is a long-term asymptotic rate of return to equilibrium after a disturbance. Again, the larger its value, the more stable the system, but now we measure the response of a long-term dynamics and not the short-term as we do with initial resilience. And finally, our last Jacobian metric is stochastic invariability, which is the inverse of the maximal response variance to white noise. So here we measure the response to white noise and not to pulse disturbance, as with all with 4 previous metrics. And again, the larger the value, the more stable the system. This is a kind of analog of invariability that Ludmila presented in the set of functional stability metrics. And now, briefly, an example of how these metrics look like when applied to our case study, where chlorpyrifos, the insecticide, as Ludmila already explained to you, was applied to reach freshwater invertebrate systems. we see that reactivity, for example, is much higher in the high concentration of insecticide, which means that the system is destabilized more. This is initial reactivity. So the system is destabilized more in the high concentration compared to the low concentration. Similarly, for maximal amplification, we see that for the high concentration, the maximal amplification is much larger compared to the low one, which means that the system is amplifying more, it's more disturbed in a higher concentration compared to the low concentration of chlorpyrifos. And as another example, perhaps if we look at initial resilience, we see that in the low concentration, the value is, there is a lot of variability between two ditches we have. We have the mean and standard deviation across the analysis for each ditch separately. So there's quite some variation, but one could say that the initial resilience is higher in low compared to the high concentration, which means that in the low concentration, the initial rate of return to a pre-disturbed to equilibrium state is faster compared to how it returns, how this community returns to the pre-disturbed state in the high concentration.
Okay, thank you very much. That was great. So many things you can do with that package. It's really hard now to think of some questions. I have a quick one to start with is the plan for this package to be kind of like this is the package and it's done, or do you guys have plans to add more features to it in the near future?
Ludmila, do you want to go?
No, I'll leave it to you.
Okay, well, I think it's a tool, and the tools are never finished. There's always a scope for improvement, and there possibility for other variants that can be added to the existing metrics. So yeah, we hope that it will be a living tool that will grow with responses and feedback that we get from users, hopefully, as they are applying it to their systems, because there's always things to get better at.
Totally. Okay, so we do have a few questions popping in. So a question from Sarah says, thanks very much for the presentation. And I have two questions. So the first question is, I understand how to compute the functional metrics for the time series experiencing short-term discrete disturbances, so things like droughts and pollution events. But can they also be applied to long-term time series affected by gradual pressures such as climate or land use change? And in that case, how would you define the baseline?
I can take this part of it, or at least part of it. So yes, you can use them. We didn't address this because of a lack of time, but we call these gradual pressures, we call them press. And we have, you can apply them you can apply the metrics to them. We have, if you look at the paper, in the table where we list all the functions, we mention, okay, how you can interpret and which metrics you can apply to a gradual pressure or not. And I would say that defining the baseline, you could think of either a system that is similar to yours that you could use as a reference, or as I said, there is that special argument where you define if you have data on that system before this pressure change started, it could be at baseline. And in worst case scenario, if you cannot define a baseline, you still can calculate some stability metrics on your current system state purely. So instead of using the log response ratio to scale the response somehow, you can take the stability metric as it is and calculate based on that. So I would suggest going to to table 1 specifically for the functional metrics and looking at which ones can be applied to press disturbance and how to interpret. And and then for the baseline is a bit more complicated. You have to look at alternatives, so to say, either before or in parallel another system. Anything to add, Victoria?
Yeah, I think so. And the second part of Sarah's question was just, would it make sense to use these stability metrics to assess the effect of a positive disturbance? So something like an ecological restoration.
I would imagine so, right? Because it's a change, and then you're going to see the response of your system. And we often we illustrate everything with this drop, and even going back to question one, we always illustrate with like a what we call a pulse disturbance because it's easier for people to imagine that you get a forest, you set fire on it, you see what happens next. But you can also think, yeah, you could have an enrichment, a restoration, and seeing how your system is changing, no? And seeing if it's stable, seeing where it's going. And then you might just need to be, yeah, you just be aware of the interpretation of that maybe going back to your, like, that the fact that your system might be becoming different from your undisturbed, quote unquote, undisturbed case might not be as bad as it is for our bad disturbance, so to say.
Cool. Nacho, your question didn't come out. Did you want
Yeah.
to mute yourself and just ask it? Or you're okay?
Okay, yes, I was typing in. Sorry, thank you for the seminar. I was wondering first about yeah. So how long the time series have to be? How many points of time to have reliable results, or that depends on the variability? I'm not sure. This is the first question. And the second question is about replicates. So if you showed in your example, you showed mean values or values of a single time series. But if I have replicate time series with from the same treatment, for example, can they be integrated to produce unique metrics, or you do it afterwards? You calculate the stability metrics on every single replicate, and then you derive a mean and an average, etc., etc. Yes, these are my burning questions, basically.
Ludmila, is it okay if I take
Yeah,
them?
sure.
So for the time series, that's a $100 question. We are planning some future research on investigating how long is long enough and for which exactly. So if we talk about Mars, it also depends not only on the intrinsic variability or stochasticity that you have in the system, but also on the model that you specify. So of course, the more complex, the more parameters you want to estimate, the longer time series you would require to to infer them. So I don't have a good and a very clear question answer to that. The only answer would be the longer the better, but I cannot give you a a minimum number of a minimum duration you would require to estimate something reliably. And for the second question, is your question about the number of replicates is it related to Jacobian or to functional stability properties? Because for Jacobian ones, it's very straightforward to include replicates. Your Z matrix will be modified. It will not have ones on the diagonal, but it will have ones so you will have several replicates. Your N will be much larger than your M, and you will be mapping your N's with M. So you will have several ones where your in the rows, I'm waving my hands here, but in fact, in the Mars manual, it's explained very nicely. And the 2 weeks ago, Ludmila and I have given also a webinar for Ecological Forecasting Initiative, and it's recorded. And there we had more time and we had more slides on actually showing how to integrate several replicates. If you are having replicated communities that you are observing under the same conditions or under the same, say, pulse disturbances, how to include them in the model specification for the Mars. Or was your question about functional stability metrics?
Yeah, no, I understand that depending on the method, yeah. But no, it's because I was thinking, sorry, I don't want to hijack, but I was thinking whether you can substitute your long time series for more replicates, for example.
I think I have a simpler answer for this, and this is what you mentioned in your own question. For the Jacobian metrics, is like Victoria said, it's in Mars and it's integrated, so to say. But for the functional ones, what we did, and I'm sorry I didn't explain it very clearly in the presentation, is actually that I calculated the metric for each replicate, and then I did a mean of all the values. So for the functional metrics, this is how you do it. You calculate for each case, and then you do a mean of them. Good.
So I was just looking at the time, and I think although we've got loads more questions and they all sound really exciting, I think we might have to end it here because I know some of us have other things we need to go off and do, and we're already late for other meetings. But thank you so much, both of you. This was an excellent talk, and obviously a really exciting topic that people are really keen to be engaged with. So people who had other questions, I mean, do feel free to drop Victoria or Ludmilla an email to ask them these questions. I think it's going to be the best thing. I would have just carried on going, but there's quite a lot of questions now, and I don't want to be mean to yeah, it's better to, I think, to cut it off now. But thank you very much, and hopefully see people again at the next time we do one of these methods live.
Thanks a
Thank you very
lot.
much.
Thank you. Bye-bye.
Bye.